So this afternoon we have Jakub from ETH who's going to tell us about observables and open closed superstring field theory. Thank you, Jakub, for coming.
But maybe I can say it now when I was prompted. About the dinner, so today we have a conference dinner at 6:30 at restaurant Nebozízek at the hill Petřín, which is like a foresty hill overlooking the downtown of Prague. It's a nice location. Unfortunately, the weather is not cooperating. So it's a place that is super easy findable using Google Maps or any of your favorite apps. But for the convenience of those who don't want to stare at the telephone and want to have a company, and maybe they don't even have a cellular data. So two Italians volunteered. One, Eugenia Boffo, is leading a group from here, about 5:30ish from here, and Carlo Macaferri can accompany those from who prefer to stop at the hotel first. Everybody else is, of course, free to choose one of them as your local guides, or reach the hotel independently. So 6:30 at the hotel. So I hope I said everything concerning. Yeah, and if you haven't signed the attendance sheet, then see Renan and sign. It's important to have your signature, to have your meal reimbursed. Thank you. Sorry, Jakub.
How about now? Okay. Okay, so many thanks again to the organizers for inviting me to give this talk, in which I will describe some joint endeavors with Carlo Macaferri, which are still yet to appear. Also, this is the first time I'm giving a talk with handwritten slides, so I hope you'll be able to read everything. So let me first briefly motivate what I'm going to do. So in general, we would like to construct observables, which would help us with identifying a classical solution in open closed superstring field theory. So that is a sort of paradigm which was heavily discussed by Carlo in his talk in the morning. So here we will typically start with a consistent background, which is given by a bulk CFT, together with a value for the closed string coupling constant, as well as an open string background encoded in a boundary state. We will formulate a tree-level truncation of a full quantum open closed superstring field theory on such a background, and given this background, we'll construct what we call classical solutions. So in Carlo's language in the morning, this capital phi star is simply a solution in, let's say, pure closed string SFT given just by the sphere diagrams, whereas this capital psi star is what Carlo called vacuum shift. So that is then a classical solution of an equation of motion which has a weak infinity structure, and which is basically given by freezing the dynamic closed string field to the classical solution phi star. So we claim, or more precisely, classical background independence conjecture claims that this set of classical solution should correspond to a new consistent open closed superstring background, which is given by some CFT hat and a new value of coupling constant GS hat, as well as some new boundary state. So in order to, as we will see, and as we have perhaps already seen in Carlo's talk, in order to find these classical solutions phi star and psi star, we only need offshore superstring disk amplitudes with at least one open string insertion. So there's been a recent work by Hiroshi Kunitomo where he actually managed to, given the so-called bosonic products or given the bosonic geometry of these open coast superstring of these open coast amplitudes, he was able to find a consistent dressing of these amplitudes with picture changing operators such that these are elevated to consistent open coast superstring field theory amplitudes. But as you will notice, there is one sort of drawback of his work, and that is that he always assumes at least one open string insertion on the disk. So one of the goals of this talk will be to extend this construction to the cases where we only have disks with or offshore amplitudes on the disk with purely bulk insertions. So as we will see, that turns out to be slightly non-trivial. So when I was talking about these classical solutions, I wasn't really specific. They can really be anything. But at the moment, when we consider a non-trivial solution to the co-string field theory equation of motion, the only sort of feasible settings where we can really do explicit calculations are the solutions which are excited by an exactly marginal deformation of the bulk co-string background. So here I name some specific examples. There's this example of moving along the Narine moduli space, which in the bosonic case is of course excited by this exactly marginal field. So that is something which we have already seen in Garov's talk. There is also the Gauss-Jordan deformation, which in the case of the bosonic string is given by this vertex operator, which is actually not a primary operator. So as Karol was discussing, that was the reason why we really need a full open closed string field theory language to describe this deformation. But then there might be also some, let's say, more interesting backgrounds, like for instance, taking an orbifold singularity and blowing it up, where at the generic point of the moduli space, we don't have an exact CFT description. So given these solutions, of course, we would like some way of characterizing these solutions. Some way of saying to which particular consistent background such a solution corresponds. So in order to be able to do that, we need to be able to construct gauge invariant quantities. So by this, I mean some functions of these solutions, capital phi star and capital psi star, which are invariant under both the gauge variation of the co-string classical solution, so that is the L infinity gauge variation, and also by the VK infinity gauge transformation of this classical solution psi star. So a particular class of gauge invariant quantities which you'll have in mind in this talk will be given by onshore amplitudes for fluctuations around these classical solutions phi star and psi star. So as you'll see, the idea will be to expand the string field around the classical solutions, substitute this expansion of the string field back into the tree-level action, so that will give us some new action for these fluctuations. And then we can use the Feynman rules dictated by this action to calculate onshore amplitudes around the shifted background. And we will see explicitly that such quantities are invariant under the gauge transformations of these classical solutions. So in order to actually be able to do some explicit calculations, we would preferably want to start with some with as simple an amplitude as possible. So here I give two examples of two sort of, I would say, simplest non-trivial amplitudes. Of course, there is the story of the 0-point amplitude on a sphere, which was discussed by Ted and which was also discussed during many of the discussions during this conference. So I will leave that aside for the moment and will focus on first the 0-point amplitude on the disk. So that's just an empty disk with no punctures, and that is basically given by this open coast tree-level action, which is evaluated on these classical solutions phi star and psi star. So again, that should ring a bell. Moreover, I will also discuss what I think is like a second simplest amplitude, and that is a disk with one co-string puncture, where of course at the puncture we need to insert an operator which is on shell, not with respect to the old BRST operator, but with respect to the shifted BRST operator around the new background phi star. So that will provide generalization of what in the context of open string field theory is known as the Elute invariant to the setting where we also can turn on a non-trivial classical solution for the closed string. So so discussion of these scattering amplitudes and how they provide observables will be like a first part of my talk. And since discussion will be mostly algebraic, I will stay bosonic in my language, but eventually we would also like to be able to compute these observables in a full-fledged RNS formulation of open coast superstring field theory. So for that, we'll need to find a way how to calculate off-shell superstring disk amplitudes with 0 open strings, in particular for the case of these two amplitudes. So that is something which I was saying was not covered by Kunitomo in his recent paper, and we'll try and see whether there is a Munich-like construction manifested in the small Hilbert space, which would give us these purely closed off-shell superstring disk amplitudes. So that much for my motivation. So as I was advertising, let me first discuss in a sort of complete generality the sort of framework of classical observables for open coast string field theory solutions. So I will start by simply writing down the tree-level truncation of the open coast string field theory action. So that is something which was carefully derived in the morning's talk by Carlo from the BV formalism. So here I just use this as a result. So the action starts, of course, with a sphere term. So the corresponding prefactor is then 1 over GS squared, and this is basically the pure co-string field theory classical L infinity action. But then we also have the disk contributions coming with the prefactor of 1 over GS, and here I divide it similarly to Carlo, the disk action into two terms. One which is given by these sort of, as I was saying, problematic vertices with only bulk punctures, and the other term which is written in terms of the open string symplectic form, that is basically the open string BPZ correlator, and that means that these vertices have to have at least one open string puncture. And then, of course, if we were to write down the full quantum microscopic open co-string field theory action, we would have higher GS terms which would describe quantum corrections. So, this action needs to be formulated on a consistent classical background. So as I was already mentioning in my motivation, by that I will understand some bulk metric plus gold CFT with total vanishing center charge. Then also some conformal boundary states, which actually in terms of these open coast products, which I use to formulate the action, roughly corresponds to the product L00. So if you look at this part of the action where I set j equal to 0, that means that I'm only keeping this phi, and this becomes a 0 product. So this will give us basically 1 point offshore disk amplitude. So that is something which we like to call boundary state, right? And then of course some value for the co-string coupling constant. So as I was saying, this is a consistent classical background. So that means that I should have a vanishing co-string sphere tadpole, so there is no L0, and I also have vanishing open string disk tadpole, so also this product M00 is set to be identically 0. There is of course an equivalent way of writing down the disk part of the action, and that is sort of turning the story around. So instead of isolating the pure closed string diagrams, I will isolate pure open string diagrams. So that is this first term, where these products, M0K, as you will see in a moment, will basically satisfy the usual relations of an A-infinity algebra. And then the rest of the diagrams is collected in this term, which is written using the closed symplectic form, and open closed products which take J closed string insertions and K open string insertions, and which have a closed string output. So of course, these are not independent. They can be defined in terms of the open closed products, which I used to write down the previous from the action, which have an open string output, these MJKs. And in particular, I define these LJKs with the closed string output by requiring that the following relation is satisfied. So on the right-hand side, I have an open string symplectic form, and now I realize there's a typo, so I can correct it in real time. There is also a psi here. It should be psi k plus 1. Right. So on the right-hand side, I have something which I know. So these are the products with the open output, and on the left-hand side, I require that that the open closed products with the closed output are fixed by requiring that this relation holds. So then after imposing the quantum BV master equation and solving order by order in GS, as was discussed by Carlo, I can derive that these products, which are defined in this way, satisfy the following homotopy algebra relations. Where the first of them are well known. This is the infinity algebra. Then this is the part of this so-called open-closed homotopy algebra of Kajura and Stashev, which has already been used by people. And then also we have this homotopy relation, which involves actually these products with which describe diagrams with purely disk puncture, with purely closed punctures, and which hasn't really been considered by Kajura and Stashev before. And it'll be actually this homotopy relation which will be interested in, mainly interested in the second part of the talk, when we construct, when we try and address these products by PCO insertions in order to be able to describe open closed superstring field theory of shell amplitudes. Equivalently, we can sort of dualize, as I was saying, this is the homotopy algebra, which mainly uses these open closed products with open outputs. We can dualize this homotopy relation again using this sort of open closed symplectic form duality, and instead give a form of these homotopy relations, which is more suited for describing closed string amplitudes. And then again, we have of course the infinity algebra for the closed strings, but then we also have the infinity algebras for the purely open products, and then we also have this non-trivial homotopy relation for which mainly involves the open closed products with the closed output. So just to give you a quick example of what these homotopy algebra relation look like when we actually evaluate them for some particular choices of these integer parameters. Yeah, so these are basically the homotopy relations saying that the fundamental open closed product commutes with the BRST operator from both sides, from both the open and the closed side. So these follow from basically from the known open closed homotopy algebra relations, which are already written down by Gajura and Stashev. But then we can also have a look at the examples of the homotopy algebra relations which are not covered by the OCHA. So the first one of them is kind of trivial, and once we know that L00 is really the boundary state, then it is also expected because we know that the boundary state needs to be BRST closed. But then we have this other homotopy relation, which, as Carlo was discussing in the morning, gives us basically the moduli space decomposition for the on-shell amplitude of two closed strings scattering on a disk. And similarly, we can continue for higher and higher examples of these homotopy relations involving more punctures. So then, what I mean by classic equations of motion, I mean if we take the action, if you take this tree of a truncation of the open closed of the quantum open closed homotopy, sorry, of the quantum open closed string field theory, this doesn't provide a consistent string field theory per se, but we can still define a notion of classical solutions, right? So we can first vary actually the pure closed string action with respect to the closed string field, and that will give us the equation of motion for this classical solution phi star. And that is determined after gauge variation, which can be written in the following form. So then the procedure is that we substitute this closed string classical solution into the disk action that gives us a weak infinity structure, as was discussed by Carlo, and gives us an equation of motion for this psi star, where the classical solution psi star then describes sort of an interpolation between the old BCFT and the new BCFT for the new CFT background given by the closed string classical solution phi star, and we call it a vacuum shift. So so then this psi star is determined not only up to the closed string, sorry, open string gauge variations with the infinity structure, but the equation of motion, of course, also implicitly depends on the closed string field. So corresponding to the classical solution psi star will also vary as we apply the gauge variation with respect to the closed string gauge parameter. So again, this is the schematic picture of what we have, where we interpolate between the old consistent open closed background to the new one using these classical solutions. And in order to be able to identify what this new background actually is, we need some observables to compute. And as I was already hinting at, there will be a particular class of observables which we'll be now interested in. And these will be provided by calculating the on-shell scattering amplitudes for fluctuations around the classical solutions phi star and psi star. And it follows then from the background independence conjecture that these should really correspond, maybe up to some future definition, to the on-shell scattering amplitudes for the open closed string field theory directly formulated in the Hilbert space for the new background. So let us do that now in detail. So we will take these, we will take the dynamical string field for the old background, and we'll expand it around the classical solutions. And we'll substitute that into the action. And eventually, after the dust settles, it turns out that we'll again obtain an action which has the same form as we started with, but now it is written in terms of these fluctuations, which I denote by lowercase phi and lowercase psi. And I also pick up some constant terms. So so there is this constant term, which is basically the on-shell sphere, pure closed string action evaluated on the classical solution. This gives us the shift in the sphere partition function, and that I was saying that I would not like to discuss now in this talk. But then we have also the shift in the disk action, um, um, which is exactly the cosmological constant, which was heavily discussed by Carlo in his talk in the morning. And then the rest of the action again has a structure of the sphere disk homotopy algebra, but now with some new products, which I denote by a star. And these new products, I call them shifted products, can be expressed in terms of the old unshifted products in the following way. So this is a little bit of a messy expression, but it can be done straightforwardly by expanding the old action around the new background and collecting terms. And the crucial property is that that these new products with a star then again satisfy the same algebraic structure, the sphere disk homotopy algebra, again with the vanishing pure sphere tadpole and an open string disk tadpole. And this basically comes about as a consequence, as a direct consequence of having satisfied the two equations of motion for phi star and psi star respectively. So using these shifted products, we can then very economically rewrite the gauge variations of the classical solutions. So first of all, we have the gauge variation of the co-string classical solution phi star, and which is then expressed in terms of this shifted product L1 star. And similarly, we can express the gauge variation in terms of the gauge variation of the open string classical solution in terms of the shifted products M10 and M01. So now let's go and calculate the on-shell scattering amplitudes for the new background in terms of the Feynman rules for the for this action S star for the fluctuations. So then, of course, for generic amplitude, the starting point for such a construction should be elements of the cohomology, which is shifted of the cohomology around the two classical solutions phi star and psi star. So we'll need to be able to find some states which I call U star and I star, where in the case of U star that needs to be closed when acting with the shifted BRS with the shifted closed string BRST operator. And similarly for A star, that will be an element of the shifted open string cohomology, so that is closed when acting with the open string BRST operator, again shifted to the new background. And so of course these states U star and A star, there will be states in the sort of old Hilbert space. I'm in this Hilbert space around the old background, but this should then correspond to some states in the Hilbert space for the shifted background. And this identification between U star and I star with this U hat and U hat in the new CFT should be provided again by comparing suitable observables. So since these states in the shifted cohomology, they are obtained by solving these equations involving the shifted products, which depend on the classical solution, we should also expect that when we apply the gauge variation of the classical solution, we will also obtain non-trivial variations of these elements of the shifted cohomology. So that is actually a nice calculation. So applying this gauge variation to these equations for the cohomology elements, we can eventually derive that in terms of the shifted products, we can express the variation of the elements of the shifted cohomology in the closed string case in this way. So this is the cubic product of the closed string field theory around the new background. And similarly, we can express in terms of these shifted open closed products the gauge variations of the element in the open string cohomology. So let me now just quickly go through explicit example of how this works. So let me consider the 3-point pure sphere amplitude around the shifted background. So that's something which we have already kind of touched upon in the morning. That's something which could maybe provide a way of measuring the change in the closed string coupling constant. So in particular, I would like to see explicitly how this thing is gauge invariant when we apply the variation with respect to the closed string gauge parameter. So what we have to do when we want to prove this, we vary with respect to first the element of the shifted cohomology, which is used to compute this amplitude. But then we also must not forget to also vary this shifted product L2 star, which also, of course, implicitly depends on the closed string classical solution. So we can then go and substitute for the gauge variations as we have derived it or as we have recorded above. And after substituting and using some basic algebra, like cyclicity properties of these products, we can indeed show that that the gauge variation of this shifted 3-point amplitude on a sphere is 0. So then, of course, if we wanted to extend this result for genetic amplitudes, we would also need to be able to say how the propagators, both open and the closed propagator, around the shifted background vary when we apply the gauge variation of the classical solutions. So by a propagator, I mean an operator. So in this particular case, I'll give an example for a closed string propagator, which when we anti-commute it with the BRST operator, this is this L1, satisfies the following equation. That means that the commutator is most identity after a projector on the closed string cohomology. So that is so here of course this is again the shifted closed string cohomology. So in order to be able to let's say discuss how the higher point amplitudes provide gauge invariant quantities, we need to be able to say how this propagator varies when we apply the gauge variation of the classical solution. So for that purpose, there is a useful tool which is called homological perturbation theory. Basically, we consider perturbation of the BRST operator around the shifted background by this bit, which I call delta omega L1 star, and this is basically the variation of this L1 star with respect to when we apply the gauge variation of the closed string classical solution. So then the machinery of what we call the homological perturbation lemma gives us this result for the deformed propagator. But of course, we only need to be able to find this variation of the propagator. I mean, up to linear order in the gauge parameter omega, so we can expand, and in the end, we obtain the following result: that the gauge variation of the propagator around the shifted background is basically given by commuting the propagator with this L2 star up to a bunch of terms which turn out to be exact in the shifted cohomology. So we can basically forget about them because they decouple from the variation of the amplitude. So I mean, yeah, if you like, you can try and run this exercise for the 4-point amplitude, and you can indeed obtain the result that is again gauge invariant. And I expect that for higher point amplitudes, there should be a nice application again of homological perturbation theory to prove this result to all orders. So of course, in practice, we want to calculate observables which are easy to evaluate. So as I was already mentioning in the introduction, these will be the 0 and 1 point amplitudes on a sphere. That's something which I would like to ignore. That's something which has been shown by TAT to be basically mostly 0 after possible contributions from the boundary of the space-time. So let us now focus purely on the disk amplitudes. So for the case of the 0-point disk amplitude, again, that was something which was the subject of Carlos' talk, and there we basically have the result that the shift in the disk partition function is computed by the disk action evaluated at the classical solutions phi star and psi star. But what I would like to focus on right now is the case of the 1-point amplitude. So that's of course very useful when we want to calculate also other boundary state coefficients of the shifted boundary state. So this disk partition function that is only able to provide us with the measure of the shifted G function, but ideally we would also like to fix the other boundary state coefficients. So so for that we need to compute the 1-point disk amplitude around the shifted background. So this is what we need to do, right? So we need to consider this boundary state or this shifted product L00 star and contract it with an element of the shifted cohomology. When we then substitute for an explicit expression for this L00 star, we obtain the following expression, which can be formally decomposed into the amplitude of the element of the shifted cohomology with the old boundary state and the rest. But this decomposition is a little bit meaningless because, as we'll see in a moment, these two terms are separately not gauge invariant, and that is basically due to the fact that that this element of the shifted cohomology also non-trivially varies when we apply the gauge transformation of the co-string classical solution. So so that really provides a way of generalizing the Elwood invariant of open string field theory to the case when we also non-trivially excite some classical solution for the co-string field theory. So there is a curious observation. Not sure if it has any deep meaning. Maybe some of you could tell me. So we can actually obtain this generalized Elwood invariant or the shifted 1-point disk partition function by taking the disk part of the action, varying it with respect the co-string field, and then at the end substituting the co-string field classical solution, the open string field classical solution, and for the variation we substitute the element of the shifted cohomology. So that's it. We can also specialize to the case where we just consider trivial co-string field theory solutions. So then this psi star will be just any other classical solution for the usual infinite equations of motion of the open string field theory, and then the expression for this shifted product L00, basically for the shifted boundary state, is as follows. And as Carlo was already commenting in the morning, this really looks like an KOZ boundary state, which is of course defined up to the terms which are exact in the shifted cohomology, which in the shifted co-string cohomology, but in the case where the co-string classical solution is 0, this shifted cohomology is the same as the original one, right? So then in the general case where phi star is not equal to 0, this L0 star should correspond in some way to this boundary state B hat of the shifted background. But as we know, this L0 star will be a state expressed in terms of the states in the old Hilbert space. So that should be sort of an image of the shifted boundary state in the old Hilbert space, which was used to define our initial background. So in order to see how it comes about that this 1-point amplitude around the shifted background is indeed gauge invariant, it is first useful to express the gauge variation of this shifted boundary state L00 star. So in the case where we apply the open string gauge variation, it turns out that that we obtain something which is exact in the shifted co-string cohomology. So then when we contract with an element U star of a co-string cohomology, we automatically get a 0 because this U star does not vary when we apply the open string gauge variation, right? On the other hand, when we take this L00 star and we apply the closed string gauge variation, we not only obtain something which is exact in the shifted cohomology, but we also obtain this bit which goes like L0 star, the gauge parameter, and then the shifted boundary state. And this shouldn't be a surprise, because this is exactly the kind of term which we need to compensate for the fact that when we contract with with the element of the shifted cohomology U star, we also need to take into account the gauge variation of the U star with respect to the closed string, with respect to the closed string gauge variation, right? So then indeed, when we consider the whole thing, I mean varying the whole one-point function around the shifted background, this sort of non-trivial contribution exactly conspires to cancel the corresponding variation of the element of the shifted cohomology, and we get a 0 as we should. So let me now quickly, before I move to the superstring part of the talk, let me now quickly run through an explicit example where we will see this whole machinery in action. So again, similar to Carlo, I will consider compactifying a bosonic string on an array lattice, whose modules I will denote as capital E. So that will be given by the sum of G plus B, and I will consider some arbitrary DP brane sitting on this Narine lattice. So then, of course, for any value of these moduli, it is known how to express the boundary state. So that can be done. In the following way, where in particular, note these coefficients omega. So this is what we call the gluing automorphism, and they should satisfy this relation with the metric G. And when we can then show that such a boundary state satisfies this what we call the Ishibashi condition, which is written in terms of the modes of the del X and also these coefficients omega, right? So again, we would like to deform this Narine modulus E to some value E hat, where the variation over the deformation we will denote by epsilon, and is given and the corresponding variation of the metric and the B field is given as the symmetric part and the antisymmetric part of the variation, respectively. Right. So we can then up to linear order in epsilon we can find the corresponding classical solution in the T-level truncation of the open closed string field theory. So here the epsilon is the margin of field which excites this deformation in the Narine moduli space. This is something which we have already seen, and just to note that in order for this solution to be consistent, we need this condition to be satisfied. So the physical meaning is that basically the D brane does not decay as we move along the Narine moduli space, and in the case of DP branes, this is always satisfied. Then we can also calculate the corresponding shifted boundary state. And in order to complete all the ingredients which we need to calculate the shifted one-point function, we should also be able to write down a element of the shifted cohomology. So this is a particular way of producing a deformation of the cohomology, which was discussed by Ashok in one of these recent papers. Strictly speaking, this formula only holds in the case where the corresponding element of the shifted cohomology does not receive corrections to its mass. So in this particular case, we will start with a zero momentum graviton, but basically not only graviton. The polarization alpha does not need to be symmetric, so it can also involve Cal-prime onyx excitation. And since we know that as we move along the Narine moduli space, the state will always remain massless, we can write down this formula for element of the shifted cohomology up to leading order in the deformation parameter epsilon. So now that we have all the ingredients, we can calculate the shifted one-point disk amplitude. The structure is now as follows. Again, if you remember, in the case of the cosmological constant or the disk partition function, the structure was basically that of a 2-point amplitude on a disk up to quadratic order. So here we have two different on-show string states. So one is giving us the deformation along the Narai moduli space, and the other one that is the zero momentum graviton. That is the state which we are using to probe the boundary state. So the result is then expressed as an on-show amplitude, but for two different external states, U and V epsilon. So then, of course, we can substitute the explicit forms of these states, and we can evaluate everything in terms of the polarizations. So remember the polarization for the graviton by which we probe the brane, that was denoted by alpha, and the polarization for the deformation parameter that was denoted by epsilon. So we get the following expression. And at the same time, we should be able to compute this amplitude directly in terms of states in the new Hilbert space around the shifted background. So these are the states which are before denoted by a hat, and for that we will need to know to which state around the shifted background this U start corresponds. So in general, that will again be given by some zero momentum massless states with some new polarization, which we denote by alpha hat, which should be almost equal to the old polarization alpha up to some correction, which will vanish as we set the deformation parameter to 0. But in general, as we will see, we'll need to include also an admixture, which is given by the Gauss dilaton. No, in general, the epsilon is not traceless. The correction to what? Delta D. No. As you'll see, it will actually depend on some combination of the of the two polarizations of epsilon and alpha, and we are not able to really say that it depends on just on the trace of epsilon or trace of alpha. Yeah. So of course, I mean, this is a question about state of the shifted about the closed-string state in the shifted cohomology. So we should be able to fix these two numbers, this alpha hat and this d hat, by computing purely closed-string field theory amplitudes. In practice, this is rather hard. So instead, we developed a little bit different strategy. So first of all, let me do the following thing. First of all, let me compare the two sides of this equation. So this is the same amplitude, but on the left-hand side expressed in terms of the states in the old Hilbert space, but on the right-hand side expressed as a correlator in the new Hilbert space. So we can evaluate the two sides. The right-hand side can be evaluated using this ansatz for the state you had, and we can compare the two sides. So after we do that, we obtain the following equality, which has the following unknowns. So first of all, we have an unknown, which is the deformation of this gluing automorphism omega. And the other two unknowns which we have are these numbers delta alpha and delta d, which parameterize the deviation of the new polarization alpha hat from the old one. And of course, initially we had no Gauss dilaton, so this d hat is said to be codirected to delta t. So the method for fixing delta alpha and delta d, which we have used, is as follows. So of course we are just on the Narai moduli space. So in principle, from BCFT calculations, we know how to calculate this delta omega t just using BCFT. So since for any finite dimensional random lattice, these delta alpha and delta d, this is just a finite set of numbers. We can sort of sacrifice a number of the branes for which we will substitute known expressions for delta omega t from BCFT, and this will use to express these coefficients delta alpha and delta d. And once we know that, we can consider any other out of the infinite spectrum of the branes to test this relation if it is consistent, right? So doing this procedure for some finite number of the branes, we can learn that there are these two following simple expressions for these deviations delta alpha and delta d of the shifted cohomology element. And we can then substitute this back into this equation. And that will give us a formula for delta omega t. So after, again, some algebraic manipulations, that gives us the following simple looking formula for the deformation of the Gouin automorphism tensor. And that can be checked that is really agrees with BCFT calculations. So so that was the first sort of bosonic part of my talk. So now let me describe how to calculate these off-shell disk amplitudes which are needed for these observables in the case of an open-closed superstring field theory. So that is, we will try and address these off-shell amplitudes with PCOs, such that again the corresponding products satisfy the correct homotopy algebra relations. So for the sake of simplicity, I will focus just on the Nevers-Schwarz sector, but we sort of suppose that that the whole construction should be easily extendable also to include the Ramon sector. So in the Nevers-Schwarz sector, the dynamical string field will be taken to be picture -1 and the dynamical open string field will be taken to be picture -1. This is valid for string field which are in the so-called small Hilbert space. So that is will require that that both of these states phi and psi will be killed by the 0 modes of eta. So then of course, since the string fields carry non-trivial picture, and since we need to correctly saturate the picture inside a symplectic form, we can easily learn that that the corresponding product in this trio truncation of the open-closed string field theory action needs to carry some non-trivial picture in order for all these vertices to be non-zero. So algebraically, the structure of this action is completely the same as in the bosonic case, but we'll somehow need to be able to find a way of addressing all these with PCOs in a consistent way. So in the case of pure closed string field theory vertices, that has been done already 7 years ago by Ted, Sebastian Konopka, and Ivo. For the case of the open-closed superstring field theory vertices, which contain at least one open pacture, that was done by Hiroshi Kunitomo this year. So in this talk, we will focus on disks with purely bulk closed string punctures. So that means we will need to be able to construct cyclic products structurally giving us this SDHL algebra in a small Hilbert space such that the corresponding homotopy algebra relations are satisfied. So this we already know. This in principle we already know, but we would like to see how this homotopy relation involving the purely closed puncture disk products arises in superstring field theory. So the input for this construction will be some picture 0 products, which are defined purely in terms of their bosonic geometry. So these states, when we feed the products with the corresponding inputs, that will be given by pure surface states. In general, in the large Hilbert space, in the large open string Hilbert space, such that when we contract in sinus-symplectic form, we will produce a bosonic geometry which gives us the corresponding off-shell bosonic amplitude. So since these products are defined purely as bosonic products, that is, they do not contain any superghost contours, we should be able to freely deform the eta contours around the punctures. So for instance, starting here with a contour around the boundary puncture, so that is a eta 0 contour around the boundary puncture, we should be able to freely move it to other boundary punctures, like here, and also to the bulk punctures where the eta 0 contour becomes an eta 0 plus. So algebraically, this means that when we act with eta 0 on the output of these open closed products, we can up to science take it inside where it acts as eta 0 plus on the closed string inputs and as eta 0 on the open string inputs. So written in a concise way, we can write it that we can say that the commutator of this eta with these products mjk is 0. But we need to remember that this eta acts as eta 0 plus on the closed string slots. So that basically means that we can consistently restrict these products M to act on the open string small Hilbert space, but and give us open string small Hilbert space open string outputs. But we don't necessarily need to require, and this is crucial, we don't necessarily need to require that the closed string is in the small Hilbert space, because the xi0 minus mode is invisible to this eta 0 plus. So in order to obtain an open string output which is in the small Hilbert space, we only need to require that the closed string is in this Hilbert space which we call HC minus, which is allowed to contain the xi0 mode. But of course, we need to require the open string inputs to be in the small Hilbert space. So as in the bosonic case, we can discuss. By the way, how much time do I have? Okay, I'll try and be as quick as possible. Okay, so similar to the bosonic case, we can sort of dualize, and instead of describing the off-shell amplitudes in terms of the open symplectic form, we can realize them in terms of the closed symplectic form by defining these products LJK. But when we write this duality in terms of the large Hilbert space symplectic form like this, we'll quickly see that there is a mismatch in the degree. So while these open closed products M, as usual, were degree odd, the corresponding dual closed string valued open closed products need to be degree even, and that is basically because the symplectic form in the open string large Hilbert space contains only one xi0 mode, whereas the closed string symplectic form contains xi0 and xi0 bar, right? So that gives us this mismatch. So the corresponding sort of dual closed string products will be degree even, and if you count correctly, they will carry an intrinsic picture -1. So then similarly, we can show that the eta 0 plus, or corresponding to the eta 0 boundary contour, freely passes through these curly L products, so that we can restrict that they act on the small Hilbert space in the open string and on this half large Hilbert space in the closed string, which contains the xi0 minus mode. However, in general, they will not commute with the eta 0 minus. So they cannot be consistently restricted to act on the full small Hilbert space of the closed string. So in order to obtain products which are genuinely in the small Hilbert space for the closed string, we actually need to act with this eta 0 minus to define some genuine co-string products, which we call our LJK with the ordinary L as a commutator of this eta 0 minus with these curly products LJK. So then, since these products ordinary LJK are manifestly eta 0 minus exact, means that they will commute with both eta 0 plus and eta 0 minus, and we can consistently restrict so that they act on small Hilbert space in both open and closed string inputs. So strictly speaking, this construction of these curly L's was only valid in the case where we had at least one open string insertion, because we started with we defined them by dualizing from the open symplectic form. So we needed this one open string insertion, but we can also analogously define corresponding products curly LJ0 with 0 open string insertions by simply requiring that they give us pure surface states in the large Hilbert space with geometry, which gives us corresponding offshore bosonic amplitudes. So and then again, the story would go the same. We would find that they generally do not commute with eta 0 minus, that they are degree even, and that in order to obtain genuine small Hilbert space products which are degree odd, we need to commute with an eta 0 minus operator. So since all these products which I was just discussing were defined in terms of pure bosonic geometry, they have to satisfy the corresponding bosonic open closed homotopy algebra relations, where in the case of these curly L products there is this minus sign which we need to be careful about, because precisely because of the fact that these L's are degree even. So one crucial thing which we need to notice about this homotopy relation is that it's basically linear in these rank parity products curly L. So in order to obtain the homotopy relation for these for the corresponding products ordinary L, which are degree odd and which are defined by commuting with eta 0 minus, we can take this homotopy relation for the curly L's and we can apply the commutator with eta 0 minus, right? Because it's linear in curly L. And then indeed we obtain the correct homotopy relation for these products ordinary L, which are genuine in the small Hilbert space, and we get the plus as we should. So that basically gives us the strategy for running the Munich construction. We can basically run the Munich construction in this Hilbert space, which is allowed to contain xi 0 minus, and we can sort of feed the picture inside the products just by using xi 0 on the boundary or xi 0 plus in the bulk. And we do this until we get the correct picture. So that will give us products which have the correct picture saturation, but which in the case of these open closed products with closed output will be these rank parity degree even products, which act on the Hilbert space containing the xi 0 minus mode, and they will satisfy this corresponding homotopy relation with a minus, but the task of getting then the genuine superstring product which acts in the small Hilbert space for both open and closed string is then very simple. We then just take the output of this Munich construction for these rank parity products, and we just commute it with eta 0 minus, and that will give us the correct homotopy algebra relation for the products which are genuine in the small Hilbert space. So I mean, the general or the construction can be done, but it's very technical and not very illuminating. So let me just very quickly run through an example where we actually construct this this open closed product L10, which is crucial for calculating the 2-point amplitude on a disk, which is important for calculating the second order cosmological constant and also the Elwood invariant. So we start with the bosonic input. So these are the following products: the BRST charge for the closed string, the 2 product for the closed string, and also the boundary state in this Hilbert space containing the xi0 minus mode, and then also the open closed product. And these will assume that they are given to us. So basically, once we construct them in the bosonic string, we use the same geometry for these input products for the whole construction, and therefore they have to satisfy this version of the homotopy relation with a minus sign again here, which is due to the wrong parity of these products curly L. And then we run the usual machinery where we construct the gauge products by basically addressing these bosonic products with the xi0 modes. Well, as I was saying, we will only use xi0 plus modes in the bulk and xi0 modes on the boundary. And we will not care about xi0 minus modes because we're constructing products in this Hilbert space, which intrinsically contains the xi0 minus mode. So we can do this the usual way. So in this particular case, we actually need 2 steps because the bosonic products, which we start with, have picture deficits too. So we need sort of 2 rounds of the Munich construction to saturate them with the correct picture. We can do this. And in the end, we obtain this product curly L10 with picture 1, which has the correct picture saturation, and which satisfies the correct homotopy algebra relation, which you would have expected from such a product curly L10. But of course, in order to obtain the final superstring product, which will enter the calculations of these offshore amplitudes, we need to project down to the genuine small Hilbert space by applying the commutator with eta 0 minus. And that gives us the following expression for the superstring product. So we can notice that the superstring product is basically given by an expression which we would have naively written down just using the Munich construction in the small Hilbert space. But there is this weird bit which is needed because this naive bit is actually not killed by eta 0 minus. So this is like a compensator term which ensures that the superstring product is genuinely in the small Hilbert space in a way which is consistent with the homotopy algebra relation. So again, as an application, we could use these products to calculate observable for open closed solutions. So let me just very quickly go through the slides since I'm heavily out of time. But the story is algebraically totally identical to the bosonic case. So again, we will consider marginal deformation of the closed string background, which will induce some vacuum shift. But this time we write everything in terms of the superstring products. So here we have this product L211. So this is a superstring product which was already constructed by Ted and Ivo and Sebastian many years ago. And for the vacuum shift, we have this product M10, which is one of the products which was constructed by Hiroshi Kunitomo because it has an open string output. So that's something which is being covered by his paper. But in order to evaluate these solutions, in order to evaluate some observables for these solutions, we will also need the purely disk products which we have just constructed. So in particular, I'll be interested in the shifted dispartition function that is into the cosmological constant, and that can be written down in terms of the superstring product L100. Here I wrote it down in sort of a compact form. So instead of writing the amplitude in terms of the 3 contributions coming from the closed string degeneration, the open string degeneration, and a piece in the middle of the moduli space, I wrote it in terms of a single product which I call L tilde, and that is basically given by the homotopy transfer of the original product L10. So by substituting this form for the L10 utility, I would have obtained the same expression as was written down by Karol in his morning's talk. So we can then expand the superstring products explicitly in terms of the insertions of the PCO and also of Xi0 contours. And we obtain an expected result, basically that the quadratic part of the shifted disk partition function is given by an expected superstring S matrix element with insertions of x0 and also x0 bar on the other state, plus terms which are localized at open and closed string degeneration. So these are terms which involve the projector on the closed string cohomology, on the open string cohomology, and then of course they will involve various insertions of the PCOs and the ghosts. So then we can of course go and explicitly evaluate these contributions for some examples of backgrounds. So using basically the same technique as was used in the bosonic case by Karol in the morning, we can explicitly evaluate this S matrix bit of the cosmological constant as an integral. But we can also actually find out that for some specific choices of backgrounds, which have n equal to Virchow supersymmetry, we don't have to calculate this integral, and it actually localizes on the boundary of moduli space itself. So combined with these terms which are already localized, you learn that the whole contribution at the second order to the cosmological constant gets localized to the boundary of the moduli space. So that is a story which has been heavily explored in recent years by Karol and Alberto Meruano, and by part also by me. So we can explicitly evaluate these things for the case of the Narayan deformation, which now is given by the following vertex operator. So this is a little bit different from the bosonic case, right? So instead of diaxis, we have these psi's and also e to the -5 bar. And we learned that the S matrix bit of the cosmological constant gives us this contribution, which goes like a trace of epsilon epsilon, whereas the localized contributions, they give us a trace of epsilon the whole thing squared plus a trace of epsilon epsilon transpose. So then when we substitute both of these results into the expression for the cosmological constant, we find that we actually reproduce exactly the same expression as we obtain in bosonic theory. So a priori, this was not expected. I mean, we could have for instance, obtained a little bit different coefficients in the deformation of the closed string coupling constant, but as it turns out, we get precisely the same thing. So I mean, yeah, of course, we should have reproduced the same deformation of the G function, because the G function of the boundary state is given purely by the bosonic part of the boundary. I mean, the Virchow bosonic part of the boundary state. So that of course made us happy, but what was unexpected is that we also reproduce precisely the same deformation of the closed string coupling constant. So again, sorry for overrunning a bit. This is my summary and outlook slide. Maybe I would just like to point out some possible ways where we could go further. So maybe one could now go further order by order in the perturbation theory in GS and try and extend this Muni construction also for diagrams with higher boundary number, or then maybe even with higher genus number. So that is of course assuming that the corresponding bosonic geometry is already given to us. We could also apply now this machinery to correspond Lie-Brane deformations in some non-trivial backgrounds. By that I mean, like for instance, putting some fraction Lie-Branes on orbifold singularities and then blowing up the singularity. So that gives us sort of backgrounds which are non-trivial, described by Virchow CFT. More precisely, the Virchow CFT is not known at the generic points in the moduli space. Also, Gepner points for generic RBLs are fall into that class. And then, of course, I mean, sure, what we did is just for the NSNS, but it should be straightforward generalizable for the Ramon-Ramon, and then it would be super interesting also to look at Ramon-Ramon deformations. So Yeah, that's it. Thank you.